In this video, we are going to work on our vectored value functions, applying this to motion in a gravitational field. You guys have seen this problem in two space before. You really do work on something being shot into the air, and then only effect on it would be gravity, meaning we have some kind of parabola type thing going through space. We are going to talk about two-dimensional motion. The three-dimensional model, I just think it's more than it's worth. If those of you that are going to be working with things flying through space, you'll deal with all that stuff in physics and actually apply the things that are going to matter, like friction and air resistance and all those other things that actually make things model the way they're supposed to be, rather than here it's going to strip everything away. Okay, so if consider an object in a plane with a horizontal x-axis, y vertical, like what I just wrote. Only force is gravity. Given an initial velocity described as a vector, so how far is it going to the right, how fast is it going to the right, how fast is it going up, and the initial position, we have that, and the velocity of the object. For t is greater than or equal to 0, we get this function. So velocity is described as the initial velocity minus, this is gravity with respect to time, and then this v naught is just your length. So that the first component there is just how fast is it going in the x direction. That doesn't change. But and then gravity is going to force our velocity to chill out, right? If this is velocity, then we're using acceleration from gravity to slow that velocity down with that negative. So that's the velocity. The position function is given here. With this is what you're used to. You're used to your y model there. You have seen that at some point, maybe in physics, physical science, or maybe your Algebra 2 course. The other thing, this is just your acceleration with time, right? How much that added to your initial spot. So a soccer ball has an initial position in meters of 0, 0, okay? When it's kicked with initial velocity of that. Okay. Find the velocity and position vector. So I'm just going to follow the formulas from above. So here's A. The velocity of this vector is going to be equal to u naught. Okay, u naught is the x velocity, so that's 30, comma, and then we got negative, okay, gravity with meters. I think that is in 9.8, if I remember. Or did that not just spit it out to me? Oh, it's because I typed it wrong. It's 9.8. Yep, 9.8. Okay, I just wanted to double check. That way you engineers didn't give the mathematician a hard time for messing that up. Okay, so I plugged in 9.8, and then plus the initial y velocity, which is 6. So the vector value function is equal to 30, negative 9.8t plus 6. Okay, there's my velocity. They also wanted position. Okay, position. Okay, it's going to be u naught, which u naught was, if I scroll back up, u naught was the x velocity, so that's 30t, plus x naught. X naught is the initial position, that's 0. And then the second component is going to be negative 1/2 times 9.8 t squared. And then plus v naught, which is your vertical velocity, times t, plus your initial condition, which is 0. I'm going to rewrite this one now to clean it up. Got 30t. What is that going to be? Negative 9 is 4.5. 4.9. Negative 4.9 t squared plus 6t. 6t. There we go. Okay, that was A. We answered both. B, for the sake of time, I'm not going to have you guys graph this. I should have taken that off. But we could. This is the trajectory there. We could graph that in our y, and it would show us what it looks like. 30t just tells me how fast it goes in the x direction as it goes through the graph. So we'll skip B here. If you'd like to see it, go ahead and graph this into y somewhere. Y equals that, and you can see the graph. All right, B. Determine the time of flight and range of the object. Okay, so I just need to figure out how long does it go till it hits the ground. So I'm going to figure out negative 4.9 t squared. I'm going to take that function that represents my vertical height, and I want to know when is it going to be 0. Because I want to find when does it take off the ground and when does it hit the ground again. Using this, I can factor out t. And then I have a zero product property. I take t and I set it equal to 0. Okay, that makes sense. It starts at time 0. And then negative 4 point time t plus 6 equals 0. If I set that now, the zero product property, I got negative 4.9 t equals negative 6. And then we just use our calculator. Let me grab mine. All right, 6 divided by 4.9. Okay, so t is equal to 1.2245. Just go 4. And then this was in seconds. Okay, so that is they answered time of flight. Time of flight is right there. They also want to know range of the object. Range is the horizontal distance. Horizontal distance. So that is the x component. So x equals 30t. Well, let's just plug in t. X equals 30 times 1.2245. And that's going to tell me the range. So 30 times, mine might be a little different because I'm not going to round, 36.7 meters. So we answered how long will it be in the air, and then how far will it travel. That was problem C. We skipped B. B is a graph. We can plug that in. I'm not going to waste your video time with that. I definitely think you can just plug it in. They want to determine the max height. So if we want to determine the max height, we take our y component. So y of t equals negative 4.9 t squared plus 6t, and we want to maximize. How we do that from calc, if you don't remember, calc 1 is I take my derivative. So negative 4.9 times 2 is a negative 9.8 t plus 6, and then I set that equal to 0, and I solve. So t is going to be negative 6 divided by negative 9.8, and I got 0.6122, rounding. That tells me the time of the max height, but if I want the actual max height, I need to plug it back into y. So y of 0.6122, okay, so it's going to be negative 4.9 times that answer squared plus 6. Making sure I plugged it in. Oh, times t again. So I got 1.8367 meters. So the height was just that. It wasn't in the air very long, so it makes sense that it didn't go very high. The initial velocity also only was shooting it up 6 per t, right? 6 per 1. So it didn't even go a whole 1, so it makes sense that it wouldn't even get up to 6 meters. Hope that makes sense. Like I said for B, just graph this as your y, and you can take a look. It's going to look something like that. Like a parabola, right? It's going to be the projection of the path of something being projected, which we have worked with for a while now.